Hello everyone. In this video, I'm going to talk about decision tree. Well, this is the code which I have written. I'm using spyder. You can use anything, but I prefer spyder. Well, I've written the code a few minutes back. You can see that time. I started from 8:30 sort of, and yeah, it took me 1.5 hours to wrap my head around this concept. So, I'm not going to code in this video. I'm going to explain the coding part and a few theoretical things here and there, which I think is important. So to begin with, I'm importing the packages, the libraries, modules, whatever you call it. It's my habit to import pandas, numpy. These are the things which I import when I start my program, when I'm thinking of doing some machine learning program. And then I'm using a decision tree in this example. So from sklearn import tree, you don't need to mug up all these things. You can get this from the sklearn decision tree documentation. Not this one actually. This one we will be using this one, but not here. Yeah, it's not given here. The previous link. This is the one. So from sklearn import trees, and then clf means the classifier is equal to tree dot decision tree classifier. We are making the classifier here, then we're fitting it. So uh, we need the tree. So from sklearn import tree, and then I will talk about this later. The other things. Okay. So let's talk about the data set. So I'm going to get a data set from UCI repository. It is one of the most famous repositories of data sets. So this is the description of the dataset. The dataset is balance. What's it called? Yeah, balance scale. So this is very simple and interesting. Actually, I thought it was some real dataset, but no. What the thing is like, um, the first column. I know it's very small, so let me bump the size a little bit. Okay, the first column is like the scale. B means balanced. R means the scale is inclined to the right, and L means the scale is inclined to the left. So what this basically that there is like this is the it's written here actually. It says that yeah, the left weight, then the left distance, and right weight, then right distance. So the second column is left weight, then left distance, then right weight, then right distance. So it's like the left weight into left distance. If it is equal to right weight into right distance, then the scale is balanced. I may be okay, excuse me. So I may be wrong, but I think this is called torque. I'm pretty sure it's called torque. Force into distance is called torque. Yeah. Okay. So distance into force, the distance into weight and distance into weight. So if the right distance into weight is more than the left one, then the scale will be inclined to the right or to the left. So this is the data set, what it means, and this is the explanation. And it says here that the class distribution is 46.8% left, 46.8% right, and 7% balanced. Okay, so this is it. Now we're going to read. Let me increase the size here also. So we are going to read this CSV using pandas with the read CSV command and putting in the URL of the repository. This URL is same as this one. You can understand this actually. It's pretty easy to understand. But after getting that data, we have to split that data into the features and the target. So y is the target and x is the feature. To split the data, the best way is to use this ILOC function. And the best way I'm saying, because there are really many features, there may be some situations when you don't want to use all the features. So in that case, instead you can just um instead of two, you just remove two like this. It can be one, three, four. It cannot be continuous. So you can just put whatever features you need for your feature list and you can be done with it. And in our example, the first column is our target, which is balanced or left or right. So .iloc, this means all the rows, and the column which I'm going to consider is 0. And for the feature part, again, nothing, then column means all the rows, and then for the feature list 1 2 3 4 means column 1, column 2, column 3, column 4. So I got my features and my target. Okay, then there's a problem here. The problem with this is I'm going to show you. I think I can show you this thing. Yeah. So the thing is, if you can see here, the first column it is R R R, then L R. So the thing is left is L R and B. These are not integers. Now the problem with this is the decision tree classifier, and almost all the classifiers they expect. Okay, let's see if we are recording. Hello. Okay. The problem is the decision tree classifier and the other classifiers like linear regression and SVM. They expect you to put in array inputs. Like for the fit function here, it should be array, 2D array. Yeah, 2D array. Actually, 2D array. Yeah. So it should be array. I don't think it's 2D array. It's an array of array, which is 2D array thing. So the point is it should be array, and x is the first parameter should be an array, the second parameter should be an array. But in our situation, our y, our target is not an array of integer. Sorry, it should be an array of integer. Our now in our case, it is not an array of integer. It is characters. Now we must convert these characters to equivalent integers. Not equivalent means just to denote them. We should convert them to integers. The so sklearn provides us with a library. It is called preprocessing, and the thing is called label encoder. So in our case, when you run this function, uh, b is labeled as 0, r is labeled as 2, and l is labeled as 1. I pulled up this page matrix, not this, so I crossed that out. So the thing is, you can find that it's called label encoder. It's Google sklearn label encoder. Just import the package from this one. Yeah, from sklearn, import preprocessing, and then label encoder or le or whatever is equal to preprocessing the label encoder. So we get in the label encoder object, and then we fit transform. So fit and then transform the y part. So we have the fit transform thing. So our y is now 0 1 2. So or like the corresponding ry, sorry, lrb is now 0 1 2. Like b is 0, l is 1, r is 2. Now we have to train, we have to split our data set into training and testing. So we can do that manually, or we can use the built-in function of sklearn, which is actually very useful, and we should not really try to reinvent the wheel. It's a good practice. Like it will be good for you if you try to reinvent the wheel, because like it will make your coding stronger. But since this function is already there, I'm going to use it, and you can use it. It's not a big deal. So the how to use the function, first you have to import this. Yeah, from sklearn.model selection, import train test split. So we import the function, and then xtrain x test, y test is equal to train test split. Then passing the x, passing the y, then the test size. My test size is 0.1, means 10% of my entire data will be assigned for testing. And random set is 0, or you can put random set anything, so it will be randomized. I didn't randomize it, but you can. It doesn't matter. The data by itself is quite random. Okay, So this function, if you know Python a little bit, this is actually a tuple. This returns a tuple, and x train, y train, um, x test, y test. Okay, x train, x test, y train, y test. We can split our data into these four tuples, and so our splitting is done. So we have x train, we have x test, we have y train, we have y test. Now we have to train our classifier. So classifier is CLF. I'm calling it CLF. You can call it whatever you want. You can call it CLF underscore decision tree, anything. So CLF is except there shouldn't be any space. So CLF is equal to this tree dot decision tree classifier. You can find this here. Decision tree classifier. Okay, let's go to this one. We'll take this one now. So decision tree classifier, and let's forget about this part. This parameters for the time being. I will talk about this. This is very important actually. And CLF dot fit, then fit x train y train, then CLF dot predict x test, and we're storing the result in y predict. And I wrote here predicting, and then test accuracy. So accuracy is equal to accuracy score y test y predict, and then printing the accuracy into 100 because it gives me a decimal. So into 100 will give me a percentage. And yeah, now we're visualizing the dataset which we don't need at this moment. And so if we run this, we will not get any errors because I have tested it and I'm not getting any errors. So as you can see here, the if you can see, yeah, this one, the accuracy is 79.3%, which is I don't like it, but for this dataset, I with this dataset and excuse me, so with this dataset and this um what's it called, with this classifier, I cannot seem to find any better accuracy than this. Okay, I followed one of the examples if from Geeks for Geeks, and they got the accuracy 74%. So compared to that, 79% is good enough, but I don't like it. Okay, so now about the parameter. The parameters are probably the most important things to discuss because they will a lot in the result. So if I run this with no parameters means a default parameter. So with the default parameter, as you can see, the accuracy is 76%. So if I put the parameters now, the accuracy will become 79%. This is called parameter tuning. So we'll be changing the parameters and see how the result differs. So the criterion is Gini. You can put entropy here. This is the manual. So you can see criterion is Gini, or it's written here entropy. Entropy is should theoretically it should give the same result, but when I run this on this dataset and keeping other things same, the entropy is getting me overall result is 77%. So I changed it to Guinea, and then you can see here minimum sample split. I'm putting it to 30. The default is 2. Um, Again, it's there in the documentation. Max sample split. Nope. What was it? Min sample. So yeah, min sample split. The default is 2. It's written here the minimum number of samples required to split an internal node. Like the decision tree, it splits based on decision. So uh, I can show this to you. I think there was a graph. Yeah. So okay, I cannot show this to you. Yikes. Oops. Okay. So okay, let's see what happens if I put in this default. So if I put in a default, it's again 76%, which is pretty bad. I mean, not bad, but obviously it's 79% is better than 76%. So if I put in minimum sample space equals 30, I'm getting 79%. So what happens is like the decision tree tries to keep on splitting the nodes, and sometimes when it keeps on splitting the nodes, the default is 2. So it means that it will keep on splitting the nodes until the number of nodes is 1. So the problem is overfitting. So this is a problem, and the solution is to increase the minimum sample split so that um, this problem overfitting is solved. So if overfitting is solved, then we'll be getting better results. So the only problem is overfitting. So just keep on changing the minimum sample split and see with which point you get a better result. So like I tested it here. If I change it to 38 and if I run it, the result is actually worse. It's 76%. I'm not getting an 80%. And so the thing is, I'm not getting 80% or better than this. So minimum sample split in this case 30 is good enough. The other thing is accuracy. So accuracy means you can calculate this manually or you can use this function. As I said earlier, there's no point in reinventing the wheel. So I use this function, and yeah, it's giving the accuracy. It is a function to give accuracy. This is a documentation here from sklearn.metrics. Import accuracy, I think. Import accuracy score from sklearn.metrics. Import accuracy score, and then um, parameters are y test and y predict. It will give you the accuracy, and then the interesting part, the visualization. Well, the problem is we cannot just use a scatter plot here because scatter plot means it has to be two parameters, x and y, but in our case there are five features, um, um like four features. So we will need a four-dimensional plane, and it's difficult to uh display that here. So we cannot do that. So uh, I'll try to figure out a way so that we can plot that, or I'll try to find out, actually not figure out, find out a way to plot this type of things. But in the meantime, what I was seeing actually, if you remember, I said earlier that the class distribution is for the left it is 46.8%, for the right it is 46.8%. So I plotted this thing out, and if you remember, 0 means balanced, and 1 means left, and 2 means R. As you can see, left and R are the same thing. It's more than 40%. 0.4 means 40%. It's more than 40% means it's somewhere around 45%, which is true because it's written here is 46%. So these bars show that the count is 46% and the count of balance is less than 10%, which is actually true. Now we can see that in a visual representation, which is much better to understand. Textual data is good enough, but if we see something visual, it's better. Well, this is not really related to decision tree, it's just a data visualization, but I found it interesting and hence I put it here. All right. Oops. Okay. So yeah, this is all. I think alpha is 0.8. Alpha just means opacity. It's for the plot. So nothing more here. So let's do something here. Let's change the test size to 2, 0.2. It means 20% test, and our result should change. Yep. Now it's 77.6% accuracies. Can you guess why? Well, if you cannot, it's pretty easy actually. The more you train, the better your model will become. So we now we are now training with only 80%. So the accuracy dropped. So let's do something. Let's train it with 95%. and our accuracy drastically improved to 84%. So the more you train, the better your model will become. This is the takeaway from this lesson, apart from the other things. Alright, this is all for this video. I hope the video did not break in between. The video does break with Google Hangout session, and this is the reason I don't like to use Google Hangouts too much. But I really did not have much time to prepare a separate video like the normal way, so I did it in this way. That's all for this video. Thank you.